Okay, so let us continue our discussion on micropump. We have talked about the acoustic micropump. Let us talk about electrokinetic micropump. We have already discussed that electrokinetic micropump operate on the principle of electroosmosis, and we have already discussed electroosmosis in the previous lectures. So here we will be briefly introducing to electroosmosis and then talk about a design problem. Okay. So we talk about electrokinetic micropump. Electrokinetic micropump. So here we have a channel which has some zeta potential, okay, and here inside we have an ionic liquid, a liquid with non-zero conductivity, and if we establish an electric field, okay, then we induce a electroosmotic flow, okay, and this electroosmotic flow velocity is given by epsilon 0. So that is the permittivity of free space, this is the dielectric constant of the liquid into zeta potential over the viscosity of the liquid into the electric field, okay. So that is the expression for the electroosmotic velocity. Now knowing the area of cross section of the channel, we can find the electroosmotic flow rate. So the electroosmotic flow rate for a rectangular channel, we have seen that the electroosmotic flow rate is given by into the area of cross section, the width into height, okay. So now let us consider a design problem. So we consider this situation here. We are talking about electrokinetic pumping network for capillary electrophoresis. So this is a typical microchannel network used for capillary electrophoresis. Normally we would have sample present in one of the reservoirs. So here we would be applying vacuum so that the sample plug comes to the junction, and then by applying a voltage between this port 2 and port 4, the sample will get separated along this channel, okay. So that is the principle of capillary electrophoresis. Here one such network is shown, and we have circular microchannel cross section that are etched in glass and have diameter of 100 micron. And how do we make circular microchannels? We can have bulk etching of silicon to have hemispherical channel, and we can bond those two such microchannel to get a circular microchannel cross section. And here all the channel lengths are shown. You can see this is 10 millimeter, this is 20 millimeter, this is 20 millimeter, and the long channel is 100 millimeter. The electrical impedance across 1 to 2 is measured. So you can measure the electrical impedance between port 1 and port 2. So that is measured to be 400 mega ohm, okay. Now the potentials at port 1, 2, 3 and 4 are given. So port 1 it is 100,000 volts, port 2 it is 1000 volts, port 3 is 1500 volts, and port 4 is 0 volts, okay. So it is also given the zeta potential of the channel material is given is minus 100 millivolt, okay, and the viscosity is 0.001 kg per meter second. The dielectric constant is 50, and the dielectric constant of vacuum is 8.854 into 10 to the minus 14 Faraday per centimeter. Now we are interested to know the direction and flow rate of electrokinetic flow in the longest channel. Okay. So, we are interested to know in which direction the electrokinetic flow is going to occur in the long channel and the what is going to be the flow rate. Okay. Now, how do we solve this? So, here we can assume that the fluid in the microchannel is homogeneous. Okay. So, we make an assumption is that the fluid in the microchannel is homogeneous, meaning the electrical properties are same throughout. Okay. So, in that condition the electrical impedance will be proportional to the channel length. Okay. And we can analyze the system as a network of resistors. So, in that case we can represent this network as an equivalent electrical network. Okay. Now, since we know the impedance between 1 to 2 that is given 400 mega ohm, we can predict the resistances assuming that the fluid is uniform throughout. Okay. That is the assumption we make. So, under that assumption we get R1 as 200 mega ohm, because from the length of this channel 1 to junction and junction to 2, so 1 to junction is having twice the length from junction to 2. Okay. So, sorry, we are measuring 1 to 2. So, this is actually port 2, this is 3. Okay. So, 1 to junction and junction to 2 have same length 20 millimeter. Okay. So, in that case each will have resistance 200 mega ohm, because the total is 400 mega ohm. So, R2 will be 200 mega ohm and R3 will be 100 mega ohm and R4 will be 1000 mega ohm. So, R3 has half the channel length. Okay. So, R3 is only 10 millimeters. So, it will be half of R1 to junction. Okay. So, that is 100 mega ohm and R4 is 10 times R3. So, that will be 1000 mega ohm. Okay. So, we can analyze the system as a resistor network. Now, if we consider the direction of the potential and current, we arbitrarily define the direction of the current and the potential. So, this is at junction 1 it is phi 1. So, this is at 2 is phi 2, this is phi 3 and that is phi 4, and we define the resistances R1, R2, R3 and R4 and the currents I1, I2, I3, I4. So, for convenience we define all the currents are coming towards the junction. Of course, that will not happen due to Kirchhoff's law. So, we will get some current are in fact in the reverse direction. Now, if we assume Kirchhoff's law for this electrical network, then we can arrive at a solution. Okay. So, we use potentials and current directions So using that we can establish the relation between the 4 currents, okay, and we can do that using the Kirchhoff's law. Okay. So we can write I1 plus I2 plus I3 plus I4. So all the currents coming towards the junction, the summation of that is going to be 0. Now phi 1 minus phi 2, so here phi 1 minus phi 2 is going to be I1 R1 minus I2 R2, because the direction of I2 is in this direction, so it will be minus I2 R2. So I1 R1 minus I2 R2. Similarly we would have phi 3 minus phi 4 will be I3 R3 minus I4 R4, and we have phi 1 minus phi 3 as I1 R1 minus I3 R3. So here we have 4 equations and we have 4 unknowns. The unknowns are I1, I2, I3 and I4, everything else is known. So if we solve the 4 equations simultaneously, we can get an expression for I4, okay. So we can solve for I4. I4 will be phi 4 minus phi 1 into R2 R3 plus phi 4 minus phi 2 into R1 R3 plus phi 4 minus phi 3 into R1 R2 divided by R1 R2 R3 plus R2 R3 R4 plus R3 R4 R1 plus R4 R1 R2, okay. So this is going to be the expression for I4, okay. So if we plug in the values, we know all the values here. So if we plug in the values, we can calculate I4 is minus 1.2 into 10 to the power minus 6 ampere, okay. So this is negative because here if we see here we have taken I4 to be in this direction, but in reality the current is going to be in this direction, okay. So that will be same as the direction of the flow, okay. So what that means is direction of I4 is in the reverse direction. So it is going from the junction towards the port 4, is in the reverse direction. Now we can find the electric field strength in the longest channel. So the electric field strength in the longest channel it is going to be phi 0. So phi 0 is the potential at the center minus phi 4 divided by L. So this is going to be I4 R4 divided by L. So you have all the values, we can substitute. I4 is going to be 1.2 into 10 to the power minus 6. So, that is from the junction towards port 4 into R4, R4 is 1000 mega ohm. So, 10 to the power 6 ohm divided by the length of the channel is 100 micron, right, sorry 100 millimeter. So, 10 to the power minus 3. So, that would be 11.9 into 10 to the power 3 volt per meter. Okay. So, that will be from the junction towards the port 4, that will be the direction of the electric field. Now, the electroosmotic mobility can be determined as, so mu electroosmotic is going to be epsilon 0 xi over eta. Okay. So, this is 50, that is the dielectric constant of the liquid that is given, and of the vacuum is 8.854 into 10 to the minus 14, 8.854 into 10 to the minus 14. So, into xi is given, which is 100 into 10 to the power minus 3, 100 millivolt, that is given, and the viscosity is 10 to the minus 3. So, that is going to be 4.43 into 10 to the power minus 8 meter square per volt second, right. So, we can find the electroosmotic flow velocity in the longest channel. So, U is going to be mu electroosmotic into the electric field, which is going to be 4.43 into 10 to the power minus 8 into 11.9 into 10 to the power 3. So, that will be 527 micron per second. Okay. So, knowing the electroosmotic flow velocity, we can find the flow rate. Okay. So, the electroosmotic flow rate is going to be, so that is in channel 4 is going to be U4. So, this is in velocity in channel 4 into the area of cross section. So, this is 527 into the area of cross section, this is 50 micron radius, pi into 50 into 10 to the power minus 6 square. So, that is going to be 248 nanoliter per minute. Okay. So, Q electroosmotic is 248 nanoliter per minute. Okay. So, that gives you an example how to solve for the electroosmotic flow rate in a typical microfluidic network when you are using electroosmosis for capillary electrophoresis applications. Okay. Now, let us talk about magnetohydrodynamic micropump. So, we talk about magnetohydrodynamic MHD micropump. Okay. So, magnetohydrodynamic micropumps work on the principle of Lorentz force. Okay. So, typically if you have a channel and you are applying a magnetic field, and you have an electrode through which you are applying the current through the fluid. Okay. So if you have a channel such that you are applying a current in the thumb direction and you are applying the magnetic field along the index finger, the force, the liquid will be subjected to a force along the middle finger. Okay. So that is the principle based on which the magnetohydrodynamic pumping works. So as you can see here, so this is the direction of the current, and this is the direction of the magnetic field. So you would have a force induced in this direction. Okay. So you can see this is the channel, this is the length of the channel. Okay. And this is the direction of magnetic field, and you have a current which is going in this direction between the two electrodes. So you induce a force F in this direction. Okay. So the magnetohydrodynamic pumping is based on the Lorentz force. Okay. So this force is called Lorentz force, that is acting on a conducting solution. So you need a conducting solution because you need to pass current through it. Okay. So the force F is going to be current into cross magnetic field. So that means force is going to be on the third direction. Okay. So current is along one direction and magnetic field along the direction 2. So this will be along the third direction. Okay, into W, right. So here I is the current and B is the magnetic flux intensity, this is the magnetic flux intensity, okay, and W is the distance between the electrodes. Okay. So there is, we can find out the expression for the pressure and flow. So the maximum pressure P max has been estimated as J into B into L. Okay. So J is the current density, okay, and B is the magnetic flux intensity which is defined here, and L is the channel length. Okay. And the maximum, the flow rate Q can be defined as J into B into pi dH4 divided by 128 mu. Okay. So that is the expression for the flow rate. So the Lorentz force, what it does is it induces a pressure gradient in the bulk of the fluid. Okay. So since it induces a pressure gradient, the flow induced because in the magnetohydrodynamic effects is parabolic in nature, okay, similar to that is encountered in pressure driven flow. Okay. So the Lorentz force acts on bulk fluids and creates pressure gradient. So the velocity profile is similar to that obtained for pressure driven flow. So the magnetohydrodynamic pump generates parabolic velocity profile similar to pressure driven flow. Okay. So that finishes our discussion on magnetohydrodynamic pump. Now let us talk about the micropump based on surface tension driven effects. Okay. So first we talk about passive capillary effects. Okay. So typically when we have a liquid droplet present on a solid surface, this is the contact line that we encounter. So here we have the surface tension between solid gas and surface tension between solid liquid and surface tension between liquid gas. Okay. So and this angle is known as the contact angle. Okay. So we can write the force balance at the interface. Okay. So if you do force balance along the interface, we can write sigma solid gas minus sigma solid liquid is going to be sigma liquid gas cos theta. Okay. So we make a component of sigma Lg in this direction, and that is what the force balance is at the contact line. Okay. So if you have a hydrophobic surface, what that means is that the surface energy between a solid gas interface is less than that between a solid liquid interface. Okay. So it does not the surface does not like liquid to weight it. Okay. If you have a hydrophilic surface, then the surface energy between a solid liquid interface is less than that between a solid gas interface. Okay. So if we have a hydrophobic surface, then the solid gas surface energy is less than the solid liquid surface energy. Okay. And if you have a hydrophilic surface, then the solid liquid surface energy is less than solid gas surface energy. Okay. So, the the contact the surface tension between the liquid gas interface can be obtained using a capillary tube experiment that we have seen in previous lecture. So, here we just briefly revisit that. So, as you can see in a vertical tube put in a liquid bath, if we do force balance at the interface, so we would say that the liquid gas surface tension can be determined by capillary rise experiment, and if we do force balance at the interface, then it will be 2 pi r into sigma solid gas minus sigma solid liquid will be delta p into pi r square. Okay. So, you can find sigma Lg as rho. So, you can express in terms of sigma Lg cos theta. So, this will be rho g into L into R divided by 2 cos theta. Okay. So, this is the expression for the liquid gas surface tension. Okay. So, here you see we have two configuration. Here the tube is connected vertically. So, this is the vertical configuration. Here the capillary tube is inserted horizontally to the liquid container. Okay. Now, this vertical capillary rise and horizontal capillary advancement have different applications. Vertical capillary rise is used when you want to collect some sample from a container using a capillary, and horizontal capillary advancement is used in case of filling of a microchannel for lab on chip applications. Okay. So, we have two cases here, the vertical tube configuration is used for sample collection, and the horizontal tube configuration is used for the self filling of microchannels. So, the self filling of microchannels in lab on chip application. Okay. So, let us look at first a case where the liquid is trying to rise in a vertical tube configuration. Okay. So, we consider passive capillary in vertical configuration. Here we do balance of different forces okay. So when this liquid column is trying to move off because of the capillary action, we can do a force balance on this liquid column, okay. So what are the different forces that are acting? We have gravitational force, then we have inertia force, we have interfacial force and viscous forces, okay. So we can write down the expression for these forces. We can write d over dt into m dx over dt minus m1 g minus 2 tau pi r 2 tau pi r into x plus x0 plus 2 pi r sigma Lg into cos theta. So this is the inertia force. So this is nothing but mass into acceleration, and as mass is changing with time, so we have d by dt outside the bracket. This one is the gravitational force, okay, m1 into g. So m1 is, where m1 is the mass of the liquid column above the outside liquid surface. So anything above, so this mass will be above this line, this mass will be m1, okay. And this is the the viscous force, and this is the surface tension force, okay. So this is the inertia, this is the gravitational force, and this is the viscous force, okay, and this is the surface tension force, okay. Here the x is the position variable, and x0 is going to be the immersed length, tau is the shear stress, m is the mass of liquid column. So total liquid column from the bottom to the top is m, and m1 is the mass of the liquid column above reservoir surface, okay. So now we can simplify this equation. We can write d by dt into rho into pi r square. So we write the expression for m, pi r square into x plus x0, right, into dx over dt will be equal to minus rho pi r square into x into g minus pi r square into dp by dx, this is the pressure gradient, into x plus x0, okay. So this is the pressure gradient, okay. So this is the viscous force, and plus 2 pi r into sigma Lg into cos theta, okay. So here what we have used So, the expression for the pressure gradient in this expression. Okay. So, now if you use Hagen-Poiseuille model for pressure drop, then you can write dp over dx, the pressure gradient can be written as 8 mu over r square into dx over dt, right. So, this is the Hagen-Poiseuille model. So, that we can substitute in this equation now. So, we get this equation, we get d square x over dt square plus 1 over x plus x 0 into dx over dt whole square plus 8 mu divided by r square rho into dx over dt, right. So, this is the inertia term and this is the viscous term, this is viscous plus g into x divided by x plus x 0, and this is the gravitational force term which will be equal to 2 sigma Lg cos theta divided by rho r into 1 over x plus x 0. Okay. So, that is the equation we have. This is the surface tension force. Okay. Now, we can obtain solution for the two extremes, one when the time scale is very less. So, it is basically the beginning of the capillary filling process, and the second time step is towards the end of the capillary filling process. So, solution can be obtained for two extremes. Okay. T tends to 0, x 0 less than x infinity. So, that is the beginning of the filling process. The second process is t tends to infinity and x infinity tends to L. Okay. So, first let us talk about the beginning of the filling process. So, beginning of the filling process, t tends to 0 and x 0 is less than x infinity, and also dx over dt at t equal to 0 is going to be 0. So, in this case the inertia and the gravitational force going to be negligible. Okay. Since you are talking about the beginning of the filling process, the fluid has just started to move. So, the inertia and the gravitational force are going to be negligible. So, the inertia and gravitational force are negligible. So, this is the general equation we work on, and for the beginning process we drop the inertia and the gravitational force from this equation, and if we do that we get this simple equation. You get 8 mu over r square rho into dx over dt minus 2 sigma Lg cos theta over rho r into 1 over x0 is going to be 0. So, we can do a conversion of variable. We can say capital X is x plus x0. Okay. So, if we say that, then we can write x dx over dt will be sigma Lg into cos theta divided by 4 mu into r. Okay. So, this is the equation we get, which is easy to solve. So, we can get the solution as this. The solution would be x is going to be sigma Lg into cos theta divided by 2 mu into t. Okay. Or we can convert back to the original variable. In that case we can say xt is going to be sigma Lg into cos theta r divided by 2 mu into t minus x0. Okay. So, what we see here is at the beginning of the filling process the displacement is going to vary as square root of t. Okay. So, the displacement of the capillary interface varies as square root of t. Okay. So, right. So, next we look at what happens at the end of the filling process. So, at the end of the filling process, since the liquid column is going to slow down and the driving force, which is the surface tension force, is going to die down, the inertia and the surface tension forces are going to be negligible. Okay. So, in the general equation we drop the inertia and the surface tension force from the equation. So, at the end of the filling process the inertia and surface tension are negligible. Okay. So, in that case we can get 4 nu over g r square into d x square over dt, okay, plus x minus x infinity is going to be 0, and here we define x infinity as x0 plus L. Okay. So, now if we consider a parameter x as x infinity minus x, and in that case we can convert this into an equation in terms of the new variable and try to solve that. We will continue with this in the subsequent lecture.